Scaling a software project introduces a core conflict: uncoordinated concurrent changes. When multiple developers edit the same files at the same time, work is inevitably overwritten, historical context is lost, and critical bugs become untraceable. Early version control systems attempted to fix this with a centralized model. While this created a single source of truth, it also created a single point of failure and a significant development bottleneck. In an enterprise environment, the stakes of a system failure are high. Without a reliable way to track every historical change, a single bad deployment can compromise an entire infrastructure with no clear path to recovery. Git functions as a distributed version control system. It eliminates the central bottleneck by ensuring every developer has a complete, local copy of the project's entire history. To prevent code loss at scale, Git operates as a mathematical state machine. It prioritizes the integrity of the total project state over the simple tracking of file edits. All local Git operations move files through 3 states: working directory, staging area, and repository. The working directory is the volatile sandbox. This is where active development is stored before it's officially recorded. Developers use the add command to select files for tracking, moving them into the staging area. This preparation zone allows developers to group specific changes before saving. Once the set is ready, the commit command triggers the process of writing those changes into the database. The repository is an immutable object database, storing the project's history as permanent snapshots. This separation forces a developer to curate history intentionally. Instead of saving every keystroke, the project history becomes a clean series of logical checkpoints. A common misconception is that version control simply records a list of line-by-line file differences over time. Instead, Git records full, independent snapshots of the entire project structure at the specific moment a commit is created. Git indexes these snapshots using the SHA-1 cryptographic hashing algorithm. This funnel takes file data and outputs a unique 40-character alphanumeric string that serves as a permanent ID. Because the hash is derived from the data itself, changing even a single character in the source text results in a completely different 40-character string. The basic Git object is the blob, storing raw file data mapped to its hash. A tree object groups multiple blobs, providing directory structure. A commit object wraps this, containing metadata and a pointer to the top-level tree. This creates a recursive chain of integrity. Because each commit references the hash of its parent and its file tree, any change to a past file would change its hash, invalidating every subsequent hash in the repository and making data corruption immediately detectable. The system's power comes from the commits pointer. Every commit stores a reference to its predecessor. This forms a directed acyclic graph, or DAG, an unbroken one-way chain representing the project's entire history. Branches are lightweight text files with a single commit hash, pointing to the leading edge of development. Branching forks the DAG, isolating experiments without duplicating files. The head pointer tracks the active branch, telling Git which commit populates the working directory. If the head pointer is moved directly to a historical commit rather than a branch label, the repository enters a detached head state, allowing for temporary inspection of previous project states. When work on a branch is complete, a merge operation reconciles the 2 divergent paths on the DAG back into a single historical sequence. A merge conflict occurs when the automated state machine cannot reconcile changes because 2 developers modified the exact same lines in a file. These conflicts pause the automation. A developer must manually resolve the differences to decide which version of the data is written into the next commit on the DAG. Because branching and merging only require moving small text pointers across the graph, these operations remain fast, even as the project grows to include gigabytes of data. This local graph must eventually synchronize across a global network of contributors. Remote repositories, like GitHub, act as central hosting nodes, maintaining the authoritative DAG. The clone command copies this entire remote database to a local machine, giving the developer a full, independent history. Developers fetch to download remote updates safely, while a pull fetches and immediately merges the data into their local branch. To share work, developers push local commits to the remote host, appending them to the central DAG. If the remote DAG has moved forward with other commits in the meantime, the incoming push is instantly rejected by the central server. The developer must pull the new remote changes and integrate them locally before their push can be accepted. This distributed model ensures that every local repository acts as a redundant backup, protecting the project from data loss if the central server fails. Advanced operations like rebasing or cherry-picking allow developers to rewrite or move specific commit nodes, providing precise control over how the history is organized. To maintain a clean database, the .gitignore file explicitly blocks temporary build outputs, logs, and sensitive secrets from ever entering the object model. In collaborative workflows, pull requests serve as the primary gateway for code. They allow teams to review changes for quality and security before they are merged into the main DAG. Pushing a commit or opening a pull request often triggers automated continuous integration pipelines. These systems run tests to ensure the new code is compatible with the existing project. These pipelines handle the heavy lifting of security scanning and deployment, allowing teams to move from code to production with high frequency and reliability. Understanding this underlying object model allows developers to navigate complex histories with precision. This mechanical clarity is what enables large teams to coordinate thousands of changes across a shared codebase every day.